Okay, so this short video is an instructional roadmap for our iterated prisoner's dilemma simulation lab exercise. Now, the prisoner's dilemma, it's a classic illustration of game theory, and it's something that you're likely to see in many different contexts. Evolutionary biology is just one. It's also a standard lesson in the social sciences, psychology, economics, international affairs, just to name a few. The issue at hand is a decision that a player has to make between two options in a one-on-one game with another player. One of the options is generally cooperative, while the other is kind of a selfish betrayal. In the original contextual framing of this problem, the situation was presented in which two individuals who are suspected of having committed a crime together are interrogated in separate rooms. Each suspect is given the same deal. If both you and your partner confess to the criminal act, you both get 6-year sentences. If you both stay silent, we'll still convict you on lesser charges, and you'll both get 2-year sentences. However, if there's an asymmetry, in other words, if one of you confesses and the other stays silent, the confessor goes free, while the silent partner goes to prison for 10 years. In explaining this to a class, we typically put up what we call a payoff matrix, showing the 4 possible combinations and the respective outcomes. Here, the units of payoff are in years in prison. Now put yourself in the position of one of these suspects and start by imagining that your partner is over in the other room confessing. Okay. Now if I stay silent, I'll get a 10-year prison term. But if I confess, it's only going to be 6 years. So if the partner is confessing, my better option is to confess. Now, you imagine that your partner is not confessing, that is staying silent. And so if you stay silent, you'll get 2 years in prison. But if you confess, you'll walk free. Again, the better choice is to confess. Clearly, the only rational thing for you to do is to confess. Meanwhile, your partner is in the other room using the same reasoning, and the outcome is a double confession every time. Presuming, of course, that the two suspects are making their decisions rationally and they're not allowed to discuss their situations with each other and strategize as a team before making their decisions. The dilemma here is in the way that there's a better outcome for both players. If both remain silent and get a minimal prison term, that's only 4 years total. Now, in spite of this better outcome being there, the process of rational decision-making leads to exactly the opposite outcome, the double confession, with each getting 6-year prison terms for a total of 12 years, which is the highest of all possible. Now, the general consensus here, and I concur with this, is that using criminals and prison sentences to illustrate this dilemma really drags the darker side of human nature into the picture unnecessarily. And so we generally opt to go with a more positive, if somewhat avaricious approach to the payoff matrix. In place of years in prison, which are kind of like negative points, we quantify payoffs in terms of gold coins, which most people are presumably happy to get. Now, using positive points means that we have to change the numbers around a bit. Instead of going free with no jail time at all, we use the highest payoff of 5 coins. This is called the temptation. Now here, instead of 2 years incarceration for, as I say, lesser charges, we'll have the next highest payoff. It's called the reward of 3 gold coins, which is good, but not as good as the temptation. Instead of 6 years for both confessing, we put 1 gold coin there. This is referred to as the punishment for the suspect's crime. And instead of the worst sentence of 10 years, it's 0 gold coins. And game theorists call this the sucker's payoff. So in addition to switching to gold coins instead of years in prison, we're also going to adopt the standard game theory terminology for the two options. Instead of staying silent, we're going to use the word cooperate. And in place of confessing to the crime, we'll use the word defect. Now, cooperate is sensible enough. This is the cooperative kind of behavior that we're interested in seeing develop. Defection is perhaps a little bit less familiar to students. You often hear this term in situations where an individual might be seeking asylum from an authoritarian government, as in, 3 members of the Cuban baseball team have defected to the US. Implicit in this is a sort of betrayal to their native land. But this context aside, defection is basically the term for the non-cooperative option in the prisoner's dilemma. It also has the advantage of starting with a different letter, a better choice in this regard than the word compete, which some of you will have seen in the Bryn Mawr simulation. And this is actually going to be really convenient for us in our discussion today. So we've changed the payoffs in this matrix from years in the pokey to golden coins, but this doesn't change a thing in terms of the dilemma. The best outcome for everybody involved occurs with mutual cooperation, but leave people to the rational decision-making process, and the only outcome you see is mutual defection every time. And that is the classical prisoner's dilemma. Now, given this discouraging outcome of the prisoner's dilemma giving rise to no cooperation, the big question is, how can we expect cooperative behavior to ever come about, to take advantage of that greater benefit to be had with mutual cooperation? Our interest in the iterated prisoner's dilemma comes from the notion that if individuals had repeated interactions with others, and they were able to identify which individuals did what with them in the past and adjust their behaviors accordingly, it would be much easier to get cooperative behaviors to arise and ultimately dominate in a society. Now here's where we get to that famous story involving Robert Axelrod. Not an evolutionary biologist, but rather a professor of political science at the University of Michigan, who solicited iterated prisoner's dilemma strategies from all of the leading experts in those fields where the prisoner's dilemma had been of interest. By strategy, I mean a set of rules that a player will use to determine what to play, either cooperate or defect, with the other players that are in the game. Now, all of these leading experts, professors and military strategists and national advisors and economists, devised their strategies and then sent them to Axelrod. Now, the strategies that Axelrod received were put into a virtual tournament in which individuals employing the various strategies underwent repeated interactions with each other for a number of iterations. Then, after a certain number of iterations, Axelrod called a stopping point, and the gold coins amassed by each participant was determined and a winner declared. Basically, this was a totally nerdy competition among the top game theorists of the day. And, long story short, there was one very successful strategy that won many of Axelrod's tournaments, and this is the one that we now refer to as tit for tat. The tit for tat strategy goes like this. On your first encounter with X, who is a specific opponent, you play cooperate. If X cooperates with you on that first encounter, then you cooperate with X the second time you encounter them. If X defects with you on the first encounter, then you defect against X the second time, and so on. Whatever X did to you on encounter N, then you do that to X on encounter N plus 1. Now, the success of this strategy is not especially surprising. It allows you to cooperate with others who are likely to cooperate with you, which can be determined based on past behavior. And this gives you the advantage of the reward of mutual cooperation wherever it's possible. Meanwhile, you'll be defecting with those who are likely to defect against you, again based on past behavior, and therefore you won't be rewarding defectors with that highest temptation payoff of 5. This will keep defectors from running away with lots of gold coins while you take the sucker's payoff, which in our matrix is the payoff of 0. In the first part of our lab exercise, we're going to simulate the histories of animals living and interacting with a membership of a small group through a period of many interactions. I'll be dividing the class into 4 equal-sized groups of 7 or 8, in which each student is assigned to one of 3 strategies. Tit for tat, T. Unconditional cooperation, C. Or unconditional defection, D. Interactions between individuals will occur at random, and we'll keep doing this long enough for every student in the group to have at least 30 interactions with the other members of their group. Now, because we set up the interactions using a random process, you'll be finding that people will be getting to 30 at different times. Some in the group will probably be well past 30 by the time the last individual reaches their 30 interactions. That's okay. The stopping point for us will be when the last member gets to 30. Just to be sure you get how this works, let's say I'm in a group with 7 other individuals. Now, if I'm a tit-for-tat player, I have to keep track of all 7 members and what they played against me in the previous encounter, so I can play the same to them the next time I have to interact with them. On the other hand, if I'm an unconditional cooperator or defector, I don't have to think at all. I just do whatever I do, cooperate or defect, unconditionally and at each interaction. If I defect and my opponent for a particular interaction cooperates, I record that I get 5 gold coins, and my opponent records that they got 0 for that interaction. If we both defect, we both get 1 gold coin, and if we both cooperate, we both get 3. Once the stopping point is reached, each individual will calculate an average gold coins per interaction by taking their gold coin total and dividing by the number of interactions, which will not be the same for everybody because we keep going until the last member gets to 30. Then we'll be reporting the average number of gold coins for each strategy in each group. This is going to be our class result. It'll go on the board and into your lab notebook. In the spirit of this being a biology class, we're going to cast this exercise as an investigation into the evolution of cooperative behavior. The scores, actually the average number of gold coins per interaction, will be thought of as proportional to fitness. Higher scores means higher rates of success in survival and reproduction. As such, if a group is seen to have one strategy getting a higher score than another strategy, we could expect the winning strategy to have a higher representation in the next generation. Maybe instead of being 0.375, that's 3 out of 8, of the population as it is in the present generation, it'll be at 0.500, which is 4 out of 8. Meanwhile, the relative proportion of the other strategies would have to be lower in the subsequent generation. By thinking of gold coin averages as fitnesses, we're going to be able to use the results of our simulation to project the microevolution of our mini populations across generations. If one strategy has a higher fitness relative to a different strategy, we expect its frequency in the population to increase, while the lower fitness strategy's frequency will decrease. By thinking in these terms, we can make projections for the expected outcomes of natural selection. For example, let's consider a group in which strategy A starts out at a much higher frequency in the population than strategy B. Maybe there's 7 A's and 1 B. If we see that strategy A has a higher fitness than B, maybe A's fitness is 5 while B's fitness is 3. That might roughly translate into A individuals leaving 67% more offspring, 5 relative to 3, which means that natural selection will be making A even higher in frequency in the next generation. And unless conditions change, we would expect A to continue to have a fitness advantage and B will continue to have a fitness disadvantage. And this will lead to the fixation of A as the only strategy in the population. In other words, driving B to local extinction. On the other hand, if you're starting with that same population, 7 A's and 1 B, and you found that B had the higher fitness, this would project a greater frequency of B in the next generation relative to this generation. And presuming that B's higher fitness is not a fluke, you would expect B to continue to increase while A, which was originally the more common type, would decrease. Now this gives us a qualitatively different projection for change under natural selection. Here, we would not expect A to eliminate B, but rather B would tend to increase against A. Now, another way of thinking about this is to ask, can a population consisting entirely of A be invaded by a small number of migrants that use strategy B? In the second of our scenarios, in which B had the higher fitness, the answer is yes. We showed that. We showed that B increases if rare because it has a higher fitness. On the other hand, in the first scenario, where A had the higher fitness, the answer would be no. Rare B would dwindle towards extinction. There's no reason to expect a successful invasion. That's enough for my pep talk here. There's more that we'll be getting to in lab, but this should be enough to set a context for a good part of our deep thinking on the iterated prisoner's dilemma results that we'll be getting.